All right, so the last couple videos have really honed into taking the derivative at a point using limits, but we need to talk about finding the derivative for any point of x. So we have this equation for the derivative, and I want to kind of explain what it is. So for any arbitrary x value, maybe I'll just have like an x squared graph here just in that first quadrant. For any arbitrary x value, just meaning like choose one is what arbitrary means. If I add an h to that, so that here's the point x plus h, I can find the slope of the secant line between those 2 points. This would be f of x plus h. This would be f of x, so I would do change in y over change in x, and then we could slide and let h go to 0 and slide this down to get the slope of the tangent line at that x value, and then this x value can be anything, so then you can plug in. Notice that this will give you a function of x, so notice there's an f prime of x, so it's not at a value, it's actually for all x values. And if you look at the bottom and you're like, well, where is the change in x coming from? If you do x plus h minus x in the bottom, notice that your x's go away and all you're left with in the denominator then is h. All right, let's look at an example here. So find the derivative of x squared minus 2x. So we're going to take the limit as h goes to 0. Of f of x plus h minus f of x all over h. All right, so f of x plus h would be x plus h squared minus 2 times x plus h. X plus h squared would be x squared plus 2xh plus h squared. And then I'll have minus 2x minus 2h. So that's my full numerator. I'll erase some of this so I have room. Okay, so x squared plus 2xh plus h squared minus 2x minus 2h. So that's my numerator piece for f of x plus h. And then I need to say minus f of x. So minus f of x all over h. All right, everything in f of x should cancel. Okay, that's one step that will always be true. Again, everything in f of x should cancel. Then I'm left with things that all have h's in them. So I'm going to factor out an h. I'm left with 2x plus h minus 2 in my numerator all over h. And then if I let h be 0, I end up getting 2x minus 2, and that is f prime of x. Now, if you look at a graph, I included a graph down here. This is the line 2x minus h. That's f prime. My original function is x squared minus 2x. A couple of things I want you to note here. Note that the minimum value of f, the vertex, would have a horizontal tangent line. Horizontal lines have slope of 0. So notice that is a 0 of my f prime. So where a function has a max or a min on the function, it's going to have a horizontal tangent line, which then tells me f prime of x must be 0 at that x value. Also, all tangent lines on this side would have a negative slope. And so notice that f prime outputs are negative values. Down here, I have my slope of 0. And then tangent lines on the other side would have positive slopes. And so notice f prime is positive over here. So just some connections graphically as to what might be going on between these two functions, because the derivative is the slope of the tangent line. So where the tangent line is 0, the graph of f prime will be 0. Where the tangent line has a negative slope, the graph of f prime will be negative. And where the tangent lines have positive slope, the graph of f prime will be positive. Maybe we write that. So if f of x is decreasing, then the slopes of those tangent lines will be negative, which tells me f prime must be negative. If f is increasing, then those slopes are positive, which tells me f prime of x must be positive. This is very important key information. All right, let's do another one. All right, find the derivative of the square root of x. So we say limit as h goes to 0 of f of x plus h minus f of x all over h. In this case, I'm just plugging into the square root function, so I'm going to go ahead and just do that here. And if I plug in 0 right now, I would have some issues, right? So whenever we have square roots, remember I have to multiply by the conjugate. And when that happens, I get rid of the square roots in the top. Like that is the magic that happens here. I'm taking this square root and this square root, let's say of star, those are the same, square root of box with a plus and a minus. Square root of this squared means this is going to just be star. This goes away, this becomes box. Okay, so what that means is I get x plus h minus x all over h, and then I have to keep this. Nothing happens here. All right, I can just go ahead and drop those parentheses. That's totally fine. These x's cancel. I'm left with an h in the top and the bottom. These h's cancel. And so when I go to plug in 0 here, I end up getting 1 over square root of x plus square root of x, 1 over 2 root x. And you can see here in the graph that I already had it. All right, so let's talk a little bit about the graphical connections here. If I have the square root function and I am looking at tangent lines here, well, the square root function is always increasing and does not have a maximum or a minimum. So if f is always increasing, its derivative must always be positive. And if f has no max or min, f prime will never be 0. I'll never have a horizontal tangent line on that graph. Additionally, as you take these tangent lines into 0, you end up having a vertical tangent line. We don't like vertical lines. Those slopes don't exist. So notice on the graph of f prime, I have a vertical asymptote at x equals 0. So those are just some connections graphically to start making between like what a derivative is as a function, and then like graphical connections as to why it just kind of makes sense as to like what the tangent lines are doing and what it means for the derivative at all the values of x.